بسم الله الرحمن الرحيم. السلام عليكم ورحمة الله وبركاته. In this video we'll discuss how to differentiate a function of two variables or a function of higher variables. And to do that, we start with first functions of one variable, and let's just recall or the definition of the derivative of a function of one variable. So if we recall, if we have a function y equals f of x, a function of one variable, the derivative of the function f at a point x0 is defined by the following limit. It is the limit as h approaches 0 of f of x0 plus h minus f of x0 over h. Of course, provided the limit exists. This is the definition of the derivative at a point x0. And we know that the geometric meaning of the derivative at a point is just the slope of the tangent line to the curve at the point x0 of x0. The geometric meaning gives us the slope of the tangent line at the point x0. From the definition of the derivative at a point, we go to the definition of the derivative as a function. And it is really just a generalization. We just replace x0, which is a specific number, to any arbitrary number, and we take it as a variable. So the definition as a function is given by this definition. It is f prime of x, limit as h approaches 0 of x plus h minus f of x over h, again provided the limit exists. This is the definition of the derivative at a point and as a function for functions of one variable. For functions of two variables, of x, y, really the situation is similar. For functions of two variables, we have two variables, x and y. So we have one derivative with respect to x and one derivative with respect to y. We have two derivatives. And the definition is really similar to the definition for functions of one variable. So let's see what is the definition here. Now for a function of two variables, if we have z equals f of xy, the derivative of f with respect to x, since we have two derivatives, one with respect to x and one with respect to y, we call the first one the partial derivative of f with respect to x, and the second one the partial derivative of f with respect to y. So we add the adjective partial for functions of two variables. The partial derivative of f with respect to x at a point x0, y0 is defined as the limit as h approaches 0 of x0 plus h y0 minus of x0 y0 over h. Look at the definition here. In the definition, notice that y0 is fixed. Y0 is fixed. Okay, fixed. So what is changing is x. x0 plus h and x0. So x changes from x0 to x0 plus h. So there is a change along the x-axis or parallel to the x-axis. So this gives us a derivative with respect to x. A derivative with respect to x. And the notation is given. Here we use f sub x. So this is derivative of f with respect to x, or partial derivative of f with respect to x at the point x0, y0. This is the derivative. Now for the partial derivative of f with respect to y, with respect to the other variable at x0, y0, again is defined in a similar manner. You have the limit of x0, comma y0 plus h minus of x0, y0 over h. Again, notice here x0 is fixed. So there is a change in y, or there is a change along the y-axis or parallel to the y-axis. If we just concentrate on y0, of y0 plus h minus of y0, this is just the derivative in math for functions of one variable. So here this is the notation is given as f, the change along y, so f sub y at x0, y0. So this is the notation for the partial derivative of f with respect to y, f sub y, f sub y. In both cases, of course, provided the limit exists. This is the definition of partial derivatives at a point. We can generalize it and we define the partial derivative of f with respect to x and with respect to y as functions. And we just replace x0, y0 with x and y. And so we have the following. So the definitions of partial derivatives as functions, we have the partial derivative of f with respect to x at xy is just f of x plus h, y minus f of xy. Again, y is fixed. And x is changing. F sub y, the partial derivative of f with respect to y, is given as limit as h approaches 0 of f of x, y plus h minus f of x, y. Again, x is fixed. And y is changing. So it is a derivative with respect to y. So this is the definition as functions. In a practice, given a function z equals f of xy, of xy. How to find f sub x and f sub y? In fact, to find f sub x, we use the definition. Notice here, to find f sub x, y is fixed. So y is not changing. So what is changing is x. So really, to look at y, since it is fixed, look at it as a constant. So to find the partial derivative of f with respect to y, to x, regard y, as a constant. And differentiate the function with respect to x. And differentiate of xy with respect to x. Using the differentiation rules of Math 101. And to find f sub y at xy, regard x as a constant and differentiate of xy with respect to y, using the differentiation rules of Math 101. This is how to compute f sub x and f sub y. So let's see, just as an example, how to compute partial derivatives. So let's take this example here. Consider the function of xy equals x squared plus 2xy minus y cubed. I want to find the partial derivative of f with respect to x at xy. So here I look at y as a constant and differentiate each term looking at y as a constant. Now, with the derivative of x squared with respect to x, it is 2x plus the derivative of 2xy with respect to x. So I look at y as a constant. So here the constant will be 2y. These are constants. So I leave them as they are. Time derivative of x. Derivative of x with respect to x is just 1. Minus. What is the derivative of y cubed with respect to x? Looking at y as a constant, well, this will be the derivative with respect to x as 0. So the answer is 2x plus 2y. This is for partial derivative of f with respect to x. The partial derivative of f with respect to y at xy, I differentiate each term looking at x as a constant, and I differentiate with respect to y. So the derivative of x squared with respect to y, well, x squared is constant with respect to y. So the derivative is 0 plus the derivative of 2xy with respect to y. Y is the variable, x is constant, so I keep 2x as a constant, and derivative of y with respect to y is just 1. Minus derivative of y cubed with respect to y is just 3y squared. So this is 2x minus 3y squared. Now let's consider the geometric meaning of the partial derivatives. And let's concentrate on the geometric meaning of the partial derivative of f with respect to x at a point x0, y0. And to see or to understand the geometric meaning of the partial derivatives, let's take the function z equals f of xy and its graph is just a surface. And let's take the plane y equals y0. It is a plane perpendicular to the xy plane and passing through the point x0, y0. y0. Now let's take the intersection of the surface and the plane. The intersection will be a curve, some curve. And the equation of this curve, it is the algebraic intersection of the two equations. So we have to solve the two equations. And the solution, just replace y with y0. So the equation of the curve of intersection is z equals f of x, y0. y0 is a fixed number. So here this is a function of one variable x. You have a curve whose function is f of x, y0, a function of one variable. It is very natural to ask about the tangent, about the slope of the tangent at this point on the curve, corresponding to x0, y0. What is the slope of the tangent? So this is the tangent at this point, x0, y0. The slope, since the curve is a function of one variable, the slope is the derivative at x0, at x0. So in that case, slope equal derivative of x, y0 at x equals x0. This is the derivative of math 101 because it is a function of one variable. So apply the definition. y0 is fixed, so the change in x of x0 plus h, y0 minus of x0. y0 is fixed. So this is the slope of this tangent line. But this limit can be easily recognized as the definition of the partial derivative with respect to x at the point x0, y0. So geometrically, this value, the partial derivative of f with respect to x at a point x0, y0, is the slope of the tangent line to the curve of intersection between the surface and the plane y equals y0. The fixed number y equal to 0. In a similar manner, we can find the geometric meaning of the partial derivative of f with respect to y at a point x0, y0. Finally, we consider notations for partial derivatives. So if we have a function z equals f of xy, the partial derivative with respect to x, the notations for this are given as follows. We use f sub x at xy. This is the first notation. Another notation is to write equals. We take the range z, right? Z sub x at xy, also. We use the following notation. It is partial f partial x. So notice this is delta in Greek. So here we use, it is like in math 101, we write dy dx. Now here for functions of two variables, we use same delta, but we write it as a tilted symbol, and it is delta. We call it partial f with respect to partial x. So this is for partial f partial x. Or we say the following: partial z partial x. Partial derivative of f with respect to x, partial derivative of z with respect to x. This is the notation for the partial derivative with respect to x. At a certain point, we write it as follows: f sub x at x0, y0, and this is z sub x at x0, y0, and partial derivative of f with respect to x at x0, y0. And this is partial derivative of z with respect to x at x0, y0. In a similar manner, the partial derivatives with respect to y, in exactly the same way. So it is f sub y at xy, or z sub y at xy, or partial derivative of f with respect to y or partial derivative of z with respect to y. And at a specific point, we just replace xy with x, y 0. So this is at the partial derivative of f with respect to y at x0, y0. This is z sub y at x0, y0. And this is partial derivative of f with respect to y at the point x0, y0. And this is partial derivative of z with respect to y at x0, y0. This is the notations usually used for partial derivatives with respect to x and with respect to y. Stop. We consider now higher order partial derivatives, or how to differentiate a function repeatedly. So let's consider the function z equals f of x, y, the first order derivative, and these are the partial derivatives with respect to x and with respect to y. And they are, the notation was given as f sub x, or which is the same thing as partial derivative of f with respect to x, and f sub y, this, which is partial derivative of f with respect to y. These are called first order partial derivatives. So when you differentiate with respect to x, you get a new function. When you differentiate with respect to y, you get a new function. This new function can be differentiated again. So let's take, for example, f sub x. This is a function of two variables, x and y. I can differentiate it with respect to x. What is the notation for that? Okay, here, this is f sub x. If I differentiate it again with respect to x, I put again just sub xx. And for the partial notation, it is second derivative, so it is second partial derivative of f with respect to x squared. So here the notation when it comes to partial, similar to the notation of functions of one variable or math 101. But also here, it is a function with respect to x. It is a function of two variables, x and y. I can differentiate it with respect to y. So it is f sub x. If you differentiate it again with respect to y, the result will be denoted by f sub x, y. So differentiate with respect to x, then differentiate with respect to y. The notation here in using the partial, it is given as follows. You are differentiating it twice. First with respect to x, then with respect to y. Partial x, partial y. Notice the direction here. In this notation, I differentiate with respect to x first, then with respect to y. So I go in this direction. But in this notation, I go backward. I first have to differentiate with the x, then differentiate with respect to y. The same thing here, f sub y, it is a function of two variables. I can differentiate it with respect to x and with respect to y. If you differentiate it with respect to x, the notation will be f sub x, y. I differentiate with respect to x, then with respect to y. Using the partials, it is the second derivative of f. Now with respect to y, then with respect to x. So this is the direction of differentiation, and here this is the direction of differentiation. If I differentiate this with respect to y again, I have f sub y, y equals second partial derivative of f with respect to y twice. This is for the second derivative. For the third derivative, well, I can differentiate each one of these a third time to get a third derivative. The notation, some examples, for example, f sub xx, I can differentiate it again with respect to x. So I get f sub x sub x sub x. The other notation, third derivative of f with respect to x cubed. I can differentiate this a third time with respect to y. So this becomes f sub x, x, y. For the other notation, it is third partial derivative of f with respect, first with respect to x twice, then with respect to y. Again, the direction of differentiation is in this manner, just like the other. One more time, for example, fxy here. If I take this, if I differentiate it again with respect to x, I get fx yx. So third partial derivative of f with respect to, first with respect to x, then with respect to y, then with respect to x, with respect to y. If I differentiate this with respect to y, so this is fx y, differentiate it again with respect to y, so I put y here. What is the notation here? This is third partial derivative of f with respect to x, with respect to y, then with respect to y. Here, if we have consecutive derivative with the same variable, we combine them. Okay. So really we write this as follows. Third derivative of f, partial x first, then twice partial derivative y squared. You differentiate with respect to y twice. You differentiate with respect to y twice. And for higher derivative, it is the same thing. Okay, just you can't find fourth derivative, fifth derivative, and etc. Now let's illustrate by an example how to compute higher order partial derivatives. So let's take this function of two variables, and let's find first derivative, first partial order derivative. So f sub x at xy. So here we look at y as a constant and differentiate with respect to x. So this is 2x y cubed minus derivative is 2 plus 0 plus 0. The derivative of the last two terms are 0. The same thing here, f sub y at x y. We differentiate with respect to y, looking at x as a constant. So x squared is constant, x squared. Derivative of y cubed is 3y squared minus 0 plus 1 plus 0. Now for higher derivatives, if I differentiate this again with respect to x, so I can f sub x, x again. So you differentiate f sub x again with respect to x. With respect to x, y is constant, I can 2y cubed minus 0. What about differentiate f sub x again with respect to y? So the derivative of f sub x with respect to y, this is 2x is a constant. When you differentiate y cubed with respect to y, you get 3y squared minus 0. So this is 6x y squared. We can do the same thing for the f sub y. You differentiate it again with respect to y. So differentiate f sub y again with respect to y. Again, this 3x squared is constant. When you differentiate y squared, you get 2y plus 0, and this is 6x squared y. I can differentiate f sub y with respect to x again. So I get fy sub x. When you differentiate it with respect to x, you get 6x y squared is a constant plus 0 plus 0. This is 6x y squared. We can continue, of course, for example, just a third order derivative. What is f sub x sub x sub x? So you are differentiating f with respect to x 3 consecutive times. So I have f sub xx, this is f sub xx. Differentiate it again with respect to x. When I differentiate this with respect to x, I get 0. If I take f sub x, y at xy, I differentiate f 3 times, 2 consecutive times with respect to x, then 1 time with respect to y. But this is f sub xx. When I differentiate it with respect to y, I get 6y. and etc. and etc. But here we notice an observation here. Maybe if you notice f sub xy and fy sub x. Notice these. F sub xy and f sub yx. You are differentiating it twice, one with respect to x and one with respect to y. But the order is different. We notice here that they are the same. They will give us the same answer. Is this always true or not? Is this always true or not? I.e., if you differentiate the same number of times for x and the same number of times for y, will the result be the same or not? Here you will see really under certain conditions, this is always true. You will get the same value. So what are these conditions? These conditions are given in the following theorem, which is a Clairaut's theorem. Let f be defined on a disk containing the point AB. If f sub xy and f sub yx are continuous in D, then the two quantities are equal at AB. So for equality, we have to make sure that the two functions f sub xy and f sub yx are continuous on a disk containing the specific point. So this is the condition under which we have the equality. Here we end up with one final note. We considered only partial derivatives for functions of two variables. In fact, this definition can be generalized to functions with 3 variables and 4 variables or any number of variables. It is the same definition and also the same notation. So let's just take functions of 3 variables. Well, if you want the notation for partial derivatives, if you want to differentiate with respect to x, well, this is f sub x then. With respect to y, f sub y. With respect to z, f sub z. To find f sub x, I look at y and z as constant. To find f sub y, I look at x and z as constant. To find f sub z, I looked at x and y as constant and differentiate with respect to z. The same thing for higher derivatives. If you say f sub x, it means differentiate f it y with respect to x, keeping or looking at y and z as constant. If I say, for example, f sub x, y, it means differentiate f it y, one first with respect to x, then with respect to y. Okay. If I write f sub x, y, z, then differentiate f 3 times with respect to x, then with respect to y, then with respect to z. If you write f sub x, z, y, it means differentiate f 4 times, first with respect to x, then with respect to z, third time, a fourth time with respect to y. The notation and the main method for computation is the same. So for functions of 3 variables or more variables, the same notation, the same technique for differentiation is used as it is used for functions of 2 variables. Okay. Now let's consider the following example. Let f of xy equals tan inverse of x plus y over 1 minus xy. Find the partial derivative of f with respect to x. Simplify your answer. So the solution here, to find f sub x, I have to differentiate the function with respect to x regarding y as a constant. And for that, I have to recall the derivative of the tan inverse. Okay. So let's recall really derivative of tan inverse of x equals 1 over 1 plus x squared. And if instead of x I have a function, I have to use the chain rule. For now, let's find f sub xy. This is f sub x at xy. I differentiate with respect to x, looking at y as a constant. And now I differentiate the tan inverse. This becomes 1 over 1 plus x plus y over 1 minus xy squared by the chain rule times the derivative of what is inside. So I differentiate what is inside with respect to x using the chain rule. So I have the following. We differentiate the fraction using the quotient rule. So this is 1 minus xy squared times the denominator 1 minus xy times the derivative of the numerator partial with respect to x. So this is x plus y minus the numerator x plus y times the derivative of the denominator with respect to x, 1 minus xy. So this is the rule for differentiating this function. Now we need to simplify one by one. So this is 1 over 1 plus x plus y over 1 minus xy squared times. This is 1 minus xy all squared. This is 1 minus xy. The partial derivative of x plus y with respect to x, this becomes 1 plus 0. Derivative of x is 1. Derivative of y with respect to x is 0. Minus x plus y times derivative with respect to x of 1, it is 0. Minus derivative of xy with respect to x, it will be y. Y is a constant, so this is just y. Multiply and simplify. So this becomes the following. 1 over 1 plus x plus y over 1 minus xy all squared. This is 1 times 1 minus xy. This is 1 minus xy. Minus x plus y times minus y. Minus with minus, I call plus. Y times x, xy. Y times y plus y squared. Y squared. Over 1 minus xy. 1 minus xy. All squared. Now this equals, it is a product of two fractions. Notice here, this will cancel. So 1 plus y squared times 1 plus y squared. So this is for the numerator. Now for the denominators, I have to multiply this with this denominator. So using the distributive property, this times 1 to be 1 minus xy squared plus this times this term. Notice the denominator here, 1 minus xy squared. So it will cancel with this denominator. So when you multiply this with this term, the denominator will disappear. And you end up with x plus y squared. X plus y all squared. So this is when you multiply the denominators. Simplify further, just try to expand. And this equals 1 plus y squared. Expand the square, this is 1 minus 2xy plus x squared y squared plus the second term plus x squared plus 2xy plus y squared. And you can see these two terms can be cancelled. These will be cancelled. So you end up with the following equals 1 plus y squared over 1 plus x squared y squared plus x squared plus y squared. Well, can we simplify further? If we can, we continue. If we can't, we stop. But here we notice really, if I take these two terms together here and the last two together, I can write them in this manner here. This is 1 plus y squared, 1 plus y squared over 1 plus y squared plus x squared y squared plus y squared. We can factor by grouping here. But here this becomes 1 plus y squared over 1 plus y squared plus x y. This is x squared plus y squared. This is x squared, so this is x squared. So now x squared is a common factor, and you get 1 plus y squared plus 1. From the denominator, I can also factor y squared, so this becomes 1 plus y squared. As a common factor, 1 plus y squared. What remains? 1 plus x squared. Now 1 plus y squared and 1 plus y squared will cancel, and we get the following: 1 over 1 plus x squared. So this is the final answer. Let's consider the following example here. Let f of xy, a function of two variables x and y, equals the definite integral from 2y plus 1 to x of sine t cubed dt. And we need to find f sub x and f sub y. Here the function is given as a definite integral, so to find the derivative we have to use the fundamental theorem of calculus of Math 102. So let me just recall the fundamental theorem of calculus. So we have the following here: derivative with respect to x of the following: integral from a to x of t dt. So from any constant to x. So the independent variable x is given as upper limit of integration. When you differentiate this with respect to x, I get only the integrand, which is f of t, evaluated at x. This is just f of x. It is the integrand evaluated at x. And also generalization of this one, dx of integral from a of t dt. But the upper limit is not x, rather any function of x. For example, u of x. So it is x squared, x cubed plus 1, any function of x. Here the function, the derivative is given. In fact, we apply the chain rule and the rule from Math 102. It is again the integrand of t evaluated at the upper limits of u of x times derivative of u prime of x, So these are the two rules from Math 102 related to fundamental theorem of calculus. Now having this, now we just go to our question here. So we have a function of two variables and we need to find f sub x. So this is f sub x at xy. Here I differentiate with respect to x regarding y as a constant. Y appears as a lower limit of integration. Y is constant, so 2y plus 1 is also a constant. So I have a constant 2x. What is the derivative with respect to x? A constant 2x. The derivative with respect to x is the integrand evaluated at x. So here just this is a constant. So it will be sine t cube evaluated at x. So you get it to automatically just sine evaluated at x هتكون x cube. Using the fundamental theorem of calculus part 1. So this is for the first one. Now for the second one here, I need to find f sub y. i.e. the derivative with respect to y. So I regard x as a constant and differentiate with respect to y. So here x is constant, but 2y plus 1 is a variable. My variable now is y. It is given as a lower limit of integration. Really, to apply one of these formulas, I have to make it upper limit of integration. So how to make it upper? Just a switch. So in this case, first f sub xy, it becomes, when you switch the limit of integration, you multiply by negative. So this is x to 2y plus 1 sine t cubed d dt. So now this is my function. I need to find f sub y at xy. I need to differentiate with respect to y regarding x as a constant. So now the constant x is an upper limit of integration. The upper limit of integration is a function of y. A function of y. It is not just y, it is a function of y. So in that case, I have to use the second formula. So here, the derivative of this, well, the minus is just a constant. I leave it, minus. Derivative of this with respect to y, it is the integrand sine. Replace ty with 2y plus 1. 2y plus 1. All cubed. Times derivative of 2y plus 1 with respect to y. dy of 2y plus 1. Using the second formula, but with respect to y. Okay. So this becomes minus sine 2y plus 1 cubed times 2, or just minus 2 sine of 2y plus 1 cubed. So this is the derivative with respect to y. Let's consider the following problem. Show that u sub xy equals u sub yx if the function u is given by e power xy. So to solve this problem, we have just to compute each side and check that they are equal. For our function here is u equals e power x y. I need to find u sub x y. So first I need to find u sub x. So this is u sub x. Differentiate with respect to x regarding y as a constant. So this is e power x y times derivative of xy with respect to x. It is just y. So this is u sub x. Now I need u sub xy. So I differentiate this with respect to y. So this is u x y. To differentiate with respect to y, look at x as a constant and differentiate. This is a function of y and this is a function of y, so we use the product rule. For the product rule, the derivative with respect to y, of course, the first e power x y times derivative of the second with respect to y, it is 1, plus the second y times derivative of the first with respect to y. The derivative with respect to y, this is e power x y. Derivative of xy with respect to y, it is just x. So this becomes e power x y plus xy e power x y. Or if you want to simplify, this is e power x y 1 plus x y. So this is u sub x y. Okay. Next, I have to find u sub y x. First, you need to find u sub y. So you differentiate u with respect to y, looking at x as a constant. So this is e power x y. Derivative of xy with respect to y, it is just x. Now differentiate with respect to x. So this is u yx. Differentiate this with respect to x using the product rule. So it is the first e power xy times derivative of the second with respect to x, it is 1, plus the second x times derivative of the first with respect to x. So this is e power xy. Derivative of xy with respect to x is just y. Simplify, this is e power xy plus x y e power x y. If we simplify further, taking e power xy as a common factor, we get 1 plus x y. 1 plus x y. Now, if you compare u sub xy and u sub yx, they are really the same. They are the same. Okay. They are equal. This completes the solution of the problem. Let's consider now the following problem. Let f of xy equals ln root x squared plus y squared. Find f sub xx plus f sub yy. Simplify your answer. So here we need to find each one and then add them to get the answer. Okay. Since we need to simplify our answer, we can in fact simplify our function first. Okay. So here the function here of xy equals ln root, which is really x squared plus y squared power half. By properties of the log, I can take the half outside. So this becomes half ln of x squared plus y squared. Notice here x squared plus y squared is positive, so there is no harm in taking half outside. Okay. Now I need to find f sub xx. So first find f sub x y. Okay. Differentiate with respect to x, looking at y as a constant. So half is a constant. Derivative of ln of this is 1 over x squared plus y squared times derivative of what is inside. We are using the chain rule with respect to x. So with respect to x, derivative of x squared is 2x plus derivative of y squared. With respect to x, this is 0. So I have 2x, and this is 2x. 2 with 2 will cancel. You get x over x squared plus y squared. So this is f sub x. Differentiate this again with respect to x. So this is f sub x at xy. Here we use the quotient rule. So this is x squared plus y squared. The denominator, x squared plus y squared, times the derivative of the numerator with respect to x. It is 1 minus the numerator times the derivative of the denominator with respect to x. This is 2x plus 0. Simplify. This is x squared plus y squared x squared plus y squared, x squared plus y squared minus 2x squared. And this is just y squared minus x squared over x squared plus y squared all squared. Okay, this is f sub xx. You do the same thing for f sub yy. First find f sub y at xy. When you differentiate with respect to y, this is half, a constant. Derivative of the ln, it is 1 over x squared plus y squared times derivative of this with respect to y. So this is 0 plus 2y. Okay. This is 2y. 2 with 2 will cancel. You get y over x squared plus y squared. This is f sub y. Again, differentiate again with respect to y. So this is f sub y at xy. Using the quotient rule, so this is the denominator squared, x squared plus y squared. The denominator, x squared plus y squared. Times derivative of the numerator with respect to y, it is 1, minus the numerator, y. Derivative of the denominator with respect to y. So this is 0 plus 2y. Simplify. This is x squared plus y squared x squared plus y squared plus y squared minus 2y squared and this equals x squared minus y squared over x squared plus y squared all squared. Now add this. When we add this, so this is f sub x plus f sub y, y at x, y. This is y squared minus x squared over x squared plus y squared squared plus x squared minus y squared over x squared plus y squared all squared. The two fractions have the same denominator, so this is x squared plus y squared squared. When you add the numerators, y squared minus y squared will cancel, minus x squared plus x squared will cancel, you get age 0. So 0 over this, you put age 0. So the sum will be 0. Now let's consider the following problem. Let f of x, y, z, a function of 3 variables, equals x over 2y plus 3z. Find the third partial derivative of f with respect to y, x, and z. Okay. In this notation, of course, the order of differentiation is in this manner. Okay. So first you differentiate with respect to y, then with respect to x, then with respect to z. This is the meaning of this notation. So you start first with respect to y. So this is partial f, partial y. So to differentiate with respect to y, I look at x and z as constant and differentiate with respect to y. One way here for this function, I can use the quotient rule. So this is the denominator 2y plus 3z all squared. Now here the denominator 2x, 2y plus 3z times derivative of the numerator, which is x, with respect to y. So it is 0 minus x times derivative of the denominator with respect to y. The derivative of the denominator is 2 plus derivative of z with respect to y, 0. So this is 0. Simplify, this becomes the following. This is 2y plus 3z squared. This is 0. This is 2x minus 2x minus 2 minus 2x. This is the derivative. Next, we need to differentiate with respect to x. Now this is now the second derivative of f with respect to y, now with respect to x. So you differentiate this with respect to x. When you differentiate with respect to x, you look at y and z as constant. And here y and z appears in the denominator. Y and z. So this is constant, the square is constant. So really, the denominator is a constant. Minus 2 over this will be again a constant. So everything here is just a constant. Okay. Times x. So a constant times x. When you differentiate with respect to x, you get just the constant because derivative of x is 1. So you get just this constant. So this is minus 2 over 2y plus 3z all squared. Because when you differentiate with respect to x, y and z are constant. So this whole thing is constant. Minus 2 is constant. This is a quantity is a constant. When you differentiate with respect to x, differentiating x is 1. 1 times the everything. So this is the derivative. Next, I differentiate with respect to z. So this is the third derivative of f, the third partial derivative of f. Now with respect to y done, with respect to x done, now with respect to z. So you differentiate this with respect to z. Now I can use the quotient rule, or if you want to simplify your work, I can use the power rule because I can write this in this manner. This is minus 2y plus 3z power minus 2. Power minus 2. Now differentiate this with respect to z, looking at x and y as constant. There is no x, but there is y, so I look at y as a constant. When you apply the power rule, the derivative with respect to z, this is minus 2, this constant, times, now this is minus 2, times 2y plus 3z, power minus 2 minus 1, this becomes minus 3. Use the chain rule, the derivative of this with respect to z. So derivative of 2y with respect to z is 0, plus derivative of 3z with respect to z is 3. Simplify. Bring this to the denominator, so this becomes 2y plus 3z power 3. What remains? We have minus 2 times minus 2 times 3. 3 times 4, 12. So this is the required answer.